This lesson is going to be about the atom, both the size of the atom, the structure of the atom, and how you can use the periodic table to figure out a lot of things about the atom. So to start off with, I'm going to show you a video so that you can get a sense of how small the atom actually is.
Atoms are ridiculous and unbelievably small. A single human hair is about as thick as 500,000 carbon atoms stacked over each other. Look at your fist. It contains trillions and trillions of atoms. If one atom in it were about as big as a marble, how big would your fist be? Well, about the size of Earth. Still hard to imagine? Let's try something different. Look at your little finger. Imagine that its tip is as big as the room you're sitting in right now. Now, fill the room with grains of rice. One rice corn represents one cell of your fingertip. Now let's zoom in on the rice corn. And now, one cell is as big as the room you're in right now. Let's fill it with rice again. This is about the size of a protein. And now, let us fill all the empty spaces between the rice corns with fine grains of sand. This is roughly how small atoms are. What is an atom made of? Let us just pretend that atoms look like this for a minute to make it easier to understand. An atom consists of three elementary particles: neutrons, protons, and electrons. Protons and neutrons bind together and form the atom core, held together by the strong interaction, one of the four fundamental forces in the universe. They are made from quarks and held together by gluons. Nobody knows exactly how small quarks are. We think they might literally be points, like in geometry. Try to imagine them as being zero-dimensional. We suspect that quarks and electrons are the most fundamental components of matter in the universe. Electrons orbit the atom core. They travel at a speed of about 2,200 kilometers per second, fast enough to get around the Earth in just over 18 seconds. Like quarks, we think electrons are fundamental particles. 99.99999999999% of an atom's volume is just empty space, except that it isn't. What we perceive as emptiness is actually a space filled by quantum fluctuations, fields that have potential energy and build and dissolve spontaneously. These fluctuations have a fundamental impact on how charged particles interact, but that's a topic for another video. How much space do the core and electrons actually fill? If you were to subtract all the spaces between the atom cores from the Empire State Building, it would be about as big as a rice corn. All the atoms of humanity would fit in a teaspoon. There are extreme objects where states like this actually exist. In a neutron star, atom cores are compacted so densely that the mass of 3 suns fits into an object only a few kilometers wide. By the way, what do atoms look like? Well, kind of like this. Electrons are like a wave function and a particle at the same time. We can calculate where an electron might be at any given moment in time. These clouds of probability, called orbitals, are where electrons might be with a certainty of 95%. The probability of finding an electron approaches zero the further we get away from the atom core. But it actually never is zero, which means that, in theory, the electron of an atom could be on the other side of the universe. Okay, wait a second. These strange thingies make up all the matter in the universe. For many dozens of known elements, you don't need many dozens of elementary particles, just 3. Take one proton and one electron, and you have hydrogen. Add a proton and a neutron, you have helium. Add a few more, you get carbon. A few more, fluorine, even more, gold. And so on. And every atom of an element is the same. All hydrogen atoms in the universe, for example, are the same. The hydrogen in your body is exactly the same as the hydrogen in the sun. Do you feel confused right now? We certainly do. Nothing on this scale of the universe makes any sense in our world, and we've not even begun talking about quantum mechanics or the particle zoo, which are even stranger. Our model of atoms has changed a number of times since we first conceived it, and the current one will certainly not be the last. So let us support scientists and research and wait for the next wave of mind-boggling new information about this strange world that is the basis for our existence.
So let's continue by talking a little bit about what the video was saying. And here we have the structure of an atom. And just to refresh what was being said is that you have a nucleus in the center of the atom, and that nucleus contains both neutrons and protons. And surrounding this nucleus, far, far away from the nucleus, you have electrons. And just to give you an analogy, if you were to place the size of an eraser in the Pac-Bell Park, which is your baseball field, your next electron is going to be at the very, very top of the stand. So if you're standing there with a pencil eraser, that's the size of the nucleus, and then the next electron is going to be at the edge of the last bleacher at the ballpark. So like they said in the video, most of atoms are actually just made up of space. In fact, one proton or one electron is about 1/2000th the size of a proton. So those electrons are really, really small, and they have some very unique features. So what I'd like to do is go through exactly how this structure is organized and how we can use the periodic table to help us determine exactly what an element, or more specifically, an atom looks like. So let's take a look at some subatomic particles we just saw. So we were saying, for our purposes, that an atom is made of protons, neutrons, and electrons. And because these things are so small, they weigh 0.00000 and 17 more zeros, 0.1 of a gram. It is so small, they've decided that they have to create their own set of units, and we call those atomic mass units. And a proton has one atomic mass unit, which we initialize as AMU. The neutron also has mass, and that also has one atomic mass unit. All right. So the next thing is that we have the electron. Remember, the electron is 1/2000th the size of a proton, and so for that reason, rather than write 0.000 and some number AMU, we consider that it is so small it is more or less having 0 atomic mass units. Of course, it does have mass because it is a subatomic particle, but it is so small we just consider it 0. Now protons, the way I like to remember it, proton starts with a P, and that P stands for a positive charge. All right, so that has a positive charge. Neutron, which sounds a lot like neutral, has a neutral charge. And so we just put down 0 charge for that. And the electron has a negative charge. And we use the negative sign to indicate that. So now let's work through a couple of other things. So what we have is, perhaps I'll go back to the very next thing. So if you were to add up the mass of the protons, the neutrons, and the electrons, you get something that is called the atomic mass. So the atomic mass equals protons plus neutrons plus electron AMUs. So their masses. That will give you the atomic mass. And you can tell this atomic mass, and for some reason they call it weight. It should be mass. You find that at the bottom of each of your boxes on the periodic table. So let's say, for example, we have carbon. Here we have the symbol for carbon being C. On the top of your periodic table box, you have the actual name of the element, and then you have a number. This atomic number equals the number of protons. And it's the number of protons that determines what type of element it is. So whenever an element has 6 protons, it is always carbon, no exception. Whenever an element has 1 proton, it is always hydrogen. If it has 8 protons, it's always oxygen. And below here you find the atomic mass. And I'm going to say mass because weight deals with gravity. This is the actual correct way of saying it. And just to remind you, the mass is the mass of the protons plus the neutrons plus the electrons. So using that, let's go ahead and use our periodic tables to work through some of these pieces of information. So carbon, we know, thanks to the periodic table, the letter is C. You have the atomic number being 6. Remember, that's the number that is above the C. The atomic mass you'll find below the C, and we can best do that by just making it a whole number for right now. So in this case, it's 12.01, but really we'll just round it to 12. Remember, I was saying that the number of protons equals the atomic number. So if I have the atomic number of 6, that tells me I have 6 protons. Now, the next piece of information. The number of protons in a neutral atom equals the number of electrons. So let's work on those first. So if I have 6 protons, that means I have 6 electrons. So the next thing is that I was saying the atomic mass is the addition of all of your electrons and neutrons and protons masses. Remember, the electrons have a 0 mass. And the protons have a mass each of 1. So I have 6 protons. That means I have 6 AMUs, mass of protons. 6 electrons don't weigh anything because they have the mass of 0. So what plus 6 equals 12? And that is 6, of course, because 6 plus 6 equals 12. And remember that each of your neutrons has the mass of 1. So that must mean if I have 6 AMUs of neutrons, I have 6 neutrons. Okay, so that's how I figure out my atomic mass. So how about working through the atomic, this chart for aluminum? Go ahead and stop the video, work through it on your notes, and then see if you have the right answer. So these are the answers you would expect for aluminum and lead. Let's move on to the next thing. So now what I want to work through is how you actually draw these diagrams. So the first diagram you're going to be drawing a nucleus, and in that nucleus we're going to be using different colors to actually label your neutrons, protons, and electrons. So in this case, I'm going to have my red dot equal my protons. I'll just write P. And lithium I see has 3 protons, so I'm going to draw 3 circles in there. All right. Now changing colors. For green, I'm going to have that be my neutrons. And it looks like I have 4 neutrons, so I'm going to put 4 little dots in my center over here. And then we know that the protons equal the number of electrons, and so I'm going to put just 3 dots on the outside. That would be what my atomic structure or diagram looks like. Now let's work through the Bohr diagram. I'm going to draw it and then explain it. For the Bohr diagram, Bohr diagrams show exactly where the probability is that the electrons are, and you may have noticed that from the video. So because the nucleus is so small, the first location where those electrons can be can also only be very small. In fact, it only can hold 2 electrons. So we call this a shell, and the first shell can only hold 2 electrons. The other shells can hold 8 electrons. If you remember, lithium has 3 electrons. So the first 2 go into the first shell. Remember, you cannot have any more after that. And then the third one goes into the next shell until you reach 8. Once you have filled the 8, then you have another shell. So carbon has 2 electrons in the inner shell and then 4 on the outer shell because it has 6 electrons.